Daniel Step, and this is my Lab 5 lab report. Let's get into it. Okay, intro and purpose. My name is Daniel, and the purpose of this lab was to throw some carts at each other on a frictionless track, and they were going to collide into each other. And we're going to figure out how much energy we lost during this experiment. So the main principles we used was the momentum principle and Newton's second law, which we'll dive into a little bit later into this lab report. So what did we find? Well, just a little brief overview. We realized we lost 3.39 joules of energy due to this collision. So we used these two principles, F net equals delta P over delta T, where P is mv. And in this experiment, there was no F net. So that means that our change in momentum is 0, meaning that our P final equals our P initial. We also used F equals ma, which is Newton's second law, which can be used to derive the velocity and position update formulas. So this is a little picture of our experiment. As you can see, we had two carts, and we threw them at each other, kind of rolled them towards each other, and then they collide and bounce back at each other. I can play that video later as well. And so our system is going to be both the carts, and there's no forces acting on the system. So there's no work done, because the surroundings would just be kind of, I guess it would be friction. So there would be a little bit of friction, and the collision would cause some noise, or some more energy loss, which is also more of the surroundings. The initial conditions, both cars are at a velocity, v1 and v2. They're both different velocities, but they're at a constant velocity at the initial, and they are not being acted on by really any other force, because the gravity and neutral force counteract. So the experiment, we throw them against each other. Let me play the video real quick. So, not sure if I can find this video. Oh, here we go.
2,
Y'all can see this. Boom, they collide. Yeah, it's pretty cool. I've definitely watched it a couple times just on my own, because it's a cool collision, and they both are noticeably slower at the end, which got me pondering. I was like, hold on a minute. I thought that they would not, like, they'd have the same energy, because energy is constant, right? Energy does not change, or energy is, what's the word? Conserved. That's weird that they're noticeably going slower. So I hit the keyboard. I started coding, whipped up this, and made this little simulation here, run the program, and simulated what happened by using these graphs. I figured out I could find the initial velocities and the final velocities and graph that. And then in my code, I said, hold up a minute. Ki would be 1/2 m1 times v1 squared plus 1/2 m2 plus v2 squared. And K final would be 1/2 m1, I guess like v1 final squared plus 1/2 m2 v2 final squared. Then delta F would be kF minus Ki to find the change in kinetic energy. And that printed out to be negative 0.397984, which is my change in kinetic energy. So there could be a little bit of potential error that I made. First of all, I think a lot of this is due to like noise and sound that was made, a little bit of heat or friction. But I definitely could have graphed it wrong. I could have made a lot of errors. I'm a clumsy guy at times. So I asked two questions. I said, what if we use more mass? What would happen to the overall loss in energy? I assume that this loss in energy is kind of a percent lost. So if you increase the mass, you'd probably lose more energy. Imagine if two planes collided. It would probably lose more energy than 0.39 joules. So what does it mean if we lost energy? I thought everything was always conserved. Well, it is. That's a great question. It is conserved. Some of that energy was turned into other forms of energy, such as heat, due to friction or noise. So it's always conserved. Don't be fooled. Thank you, and have a great day.